This is an example on curve of intersection problems. Curve of intersection. This is my version of an example that kind of merges section 13.1, where we discussed explicit and implicit surfaces, and it merges also section 12.1, where we're starting to talk about vector valued functions. Okay, so let's take a look at a typical example here. So this is an example on the easy side. So let me consider these two expressions. Let's consider these two expressions that we're going to write down. X plus y plus z equal to 4, and 6y is equal to negative 4x plus 2z plus 2z. Okay, the question is, so we can take these two objects and they would form a set or subset of R3, okay, because we have x, y, z, three variables, such that x plus y plus z is equal to 4, and the x, y, z values have to satisfy this equation also, the second equation. Okay, what kind of object is this set S? It is a subset of R3, x, y, z. Okay. The first object here, x plus y plus z is equal to 4. Hopefully you've plotted enough implicit functions to know that this is just the equation of some sort of plane. Okay, so there's your first object. So if you just left it at this, x plus y plus z equals to 4, you would have a subset which is the plane in R3. But since there is another object, another plane, we have to have both of those equations true. So the set of all x, y, z values that satisfy both of these equations is essentially the curve which lies in both of the surfaces, which in the case of two planes is going to be some sort of curve. This is what we are looking to describe. Here is our curve of intersection. Okay. This is our curve of intersection. Okay. And because it's a curve in three-dimensional space, we know that we should be able to describe that curve in terms of section 12.1 as some x of t, a y of t, and a z of t. Okay. So the question is, what actual expressions for x, y, and z as a function of a single variable t do we choose? Okay. Now, so let's consider the following. We need to reduce these two equations down to a single variable, and I will show you kind of how this process works. So let's take this first equation, and let's take the other equation. 6 is equal to negative 4x plus 2z. Okay. You're probably used to solving for z, so why don't I just go ahead and do that. 2z is equal to 6y plus 4x. Solving for z, that would give you 3y plus 2x. So if you solve for z, this is what you will get. Because that is equal to z, you can use that in this equation. Okay, you can make a substitution and reduce this equation down to only two variables. So this equation, once you make the substitution, this is subs, once you make that substitution, you'll get x plus y. And at the moment, we're just kind of following our nose. We're just kind of doing what you would think to maybe try, and I'll show you how it leads to the solution in just a second. So take a look here. Now we have an expression that has only x, y's, and z's. So this is 3x plus 4y is equal to 4. Okay. And then you could solve this for one of the variables. Typically we're used to solving for y. You don't have to. You could solve for x, but we're used to solving for y. So why don't we do that? That will give you 4y is equal to 4 minus 3x, and y is equal to 1 minus 3/4 x. Okay. Okay. So, what do we have here? Here we have y in terms of a single variable. Y is in terms of a single variable. You could leave that single variable as x, or we could call x is equal to t, because we're trying to describe our function, vector valued function, in terms of one variable. So why don't you just let x is equal to t. Okay? If x is equal to t, then that says that y is equal to 1 minus 3/4 t. Okay? So there's your y variable, y of t. Okay? And the last thing we have to do is to solve for z in terms of t. Well, z, right, if x is equal to t, then and y is equal to 1 minus 3/4 t, and x is equal to t, you now have z in terms of t. So that would be 3 minus 9/4 t plus 2t. Okay. Getting that into a single expression that is of the form, what is this, 8t over 4? So that would be 3 minus 1/4 t. So there's your z entry, 3 minus 1/4 t. Okay. It is a vector valued function in one variable. That variable is t. Our x variable is equal to t. So I should be able to plot this function using contour plot 3D. I should be able to plot this one with plot 3D, the other plane with plot 3D because it's explicit. And I should be able to plot this curve of intersection using parametric plot 3D. Okay, so let's put these three plots together into a single Mathematica plot and see if our curve of intersection is correct. It should look something like the following here. The following plot here. We're just drawing our sketch, but it should look something like that. So let's bring in Mathematica and plot each of these surfaces, and then we will see what we get. I'm just writing down on my sheet of paper these three equations, and then I will bring in Mathematica. Okay, so let's bring in Mathematica now. It's on the next page. Okay, so there are three plots to show. There's the first, let me make the font a little bigger here. Okay, three plots. We'll call it plane number 1. Okay, let's plot that as a contour plot 3D. Contour plot 3D, and the plane was x plus y plus z. Oops, sorry, x plus y plus z equal to 4. And let's plot this in the. Let's plot this from, say, -3 to 3. There's no reason why I'm choosing this, just taking a guess, and let's see. We can adjust it later if need be. Okay, and let's call this plot plane number 1. Okay. Semicolon to hide the output, because we'll put the output together into a show command in a second. Let's put plane number 2. Okay, and we'll call this plane number 2, and that plane is going to be plotted with a plot 3D command because it was an explicit function, and it was z is equal to 3 times y plus 2 times z, and 3 plus y plus 2 times x. Sorry about that. 3 times y plus 2 times x, and let's say that x goes from -3 to 3, and y goes from -3 to 3. There's our second plot. Now let's plot the curve of intersection. It is a 3D vector valued function in one variable. So t was my one variable, and I need to put in 3 entries here. The first entry is x of t, that would be t. The y entry would be 1 minus 3/4 times t, and the z variable is 3 minus 1/4 times t. Okay. So there's r of t, and we want to parametric plot 3D that. Plot r of t, and let's plot t from, and again this is just a guess until let's go from -1 to 1. Okay. Notice that when t is equal to 0, you'll get the point 0, 1, 3. When t is equal to -1, you'll be at the point -1. 1 plus 3/4 would be 7/4. 1 plus 1/4 would be whatever that is. Yes, whatever that is. So you could plot in different values of t, and you could get your point in 3D space. So let's call this plane plot. Okay. And let's put each of these plots together. Let's say show plane 1, plane 2, and then, oh, this is not a plane plot. I'm sorry, this should be curve plot, curve of intersection plot. Let's call this curve plot. Okay. Shift return, and here we have our 3 surfaces, and that little blue line there is your line of intersection. So notice that it's only a little line, it's only a segment of it. If I increase the plot time for, say, 2 seconds, notice that we got more of the blue curve to show up. And let's go to 4. And there is your curve of intersection, that blue line. And it does lie on the intersection of those two, so I feel pretty comfortable that I've done all my algebra correctly. Notice that we are only, let me see, plane plot. If you give this, the first plot in your list, if you give this axes label, put the plot options on the first plot in your list, we should see our axes label. And here I think we're seeing z going from, say, z is going from -3 to 3. Right. So you could adjust the plot window, but I think that is our curve of intersection. Okay. I do want to stress here that this curve here is not the only curve you could have obtained. This is not a unique answer. Each of us could get something different. You could get something different by going back to your computations. And here, for example, you could have taken this and just solved for y. And then you would have found y in terms of x and z. And then you would have plugged in y into this equation. And then possibly z could have come out. You could have solved for x in terms of z. And then z would have been your t variable. So you could have had a t here for z. And then you would have had to solve for x and y in terms of that variable t. So each of you could have there's several different choices here, or infinitely many answers, but I'll leave you to find one. So that's an easy curve of intersection problem. In the next video, would be a medium difficulty. With the intersection of a cylinder and a plane. And we know that it's going to be, the curve of intersection is going to be some slanty circle. Okay, so we'll look at that in the next video.